hope that my is done. Okay, right. Let me first see if all the scribes are present. ID number 69,
Present, sir.
ID number 70,
Present, sir.
71, 72, 73, 74, 71, 70, ID number 71, are you there? 72, 73, 74, 75, oh sorry, 75 is okay. Right, let's get started. Okay. So this is the theorem we did in the last class, right? It's the second theorem of our course. It's called the first isomorphism theorem. Says that for any groups G1 and G2, if we have a homomorphism F going from G1 to G2, then there is a way in which we can convert this homomorphism into an isomorphism. Okay, so let's say K is the kernel of this homomorphism. And we showed in the last class that the quotient group of G1 with the kernel K is isomorphic to the range of your homomorphism in the group G2. Okay, any doubts with this? Let's take a couple of examples. So would somebody care to give me an example of two groups and a homomorphism between these two groups? Anyone?
D3 and S3.
Okay. It's going to be a very interesting example, but still, let's try that. D3 to S3. And can you define the homomorphism?
Identity maps to identity.
Right, that is given then. D3 and S3, what are the elements?
I R1 R square.
Okay, I have R square.
FF BFC.
C. S3 is your identity.
1, 2, 3. 1, 3, 2.
1 2 2 3 3 1 3.
So I'm assuming this is a homomorphism, right? I hope you have verified this, in the sense that the group tables should be the same If you relabel according to this scheme, if you do that, then this becomes a homomorphism. In fact, this is, what is this map? It's just a homomorphism.
Bijective.
Isomorphism as well.
This is an isomorphism, right? In fact, that is what I meant when I said this example as such is not very interesting. Why? Because what is the kernel of F?
Just I.
Identity.
Just I. Okay, and moreover, what is FG1? This G1 is B3. What is the range? It's equal to your codomain, obviously, is 3. Okay, so then what is G1 slash K? It is G1, right? And therefore, in this F, and of course FD3, so G1, sorry, patience from the example. G1 is D3, D3 slash quotient with just the identity is nothing but D3, isn't it? It's like, again, carrying forward the analogy between integer division and quotient groups. And this is like division by 1. Okay, so it doesn't really give you anything. It's the same number. Okay, so this is D3 and D3 is isomorphic to S3 using this function efficiency. Any doubts in this example? In fact, I was sorry. So yeah, in the analogy with the integer division, this is basically like dividing a number by a number which is greater than that. Okay, so in that case, we know the remainder will be the original number itself. Okay, because integer, sorry, division by 1, the remainder will always be 0. So that is if the kernel, so in the case your homomorphism is a trivial, so maybe that's an interesting example. Let F is G1 to G2 and F G1, let's say, is E2, right? The identity element in G2. In this case, what is the kernel?
G1.
G1. Then G1 quotient group kernel F would be
Identity.
would it be the identity element? What would be the only coset?
G1.
G1 itself, but considered as a single element. Okay, so this is analogous to division by 1. Okay, no matter what your number is, the remainder will always be only 0. Okay, so in that sense, all integers are equivalent. Here, it's like all group elements are equivalent. Okay, whereas the previous case is like divide any number of your group by some larger number. Okay, so in that case, the remainder will be the element itself. All right. So please don't get mistaken here. When I say D3 quotient identity is D3, I don't mean D3 is one element. Okay, each element of D3 is a separate coset. Okay, so don't get confused between this and this.
Sir, so isn't it that D1 quotient group of D3 with respect to identity will be analogous to division by 1.
Once again,
Sir, here in second example, you said that it is analogous to division by 1. But
yes.
sir, it seems like in first example it is analogous to division.
No, so okay, let's take any integer, divide it by 1. What is the remainder?
0.
0 only, right?
Yes,
See,
sir.
what are you doing when you're taking quotient groups? Right? All equivalent elements, you're considering it as only one element, isn't it? Yes?
Yes, sir.
So in the second example, how many different equivalent elements are there? All elements of the group belong to one coset, isn't it?
Yes, sir.
So therefore, all elements of the group are one and the same.
Only one equivalent. Yes.
Exactly. That is why I'm saying it is analogous to division by 1. Okay, because when you divide, you look at Z and you divide by 1 and look at the remainder, all elements will give the same remainder 0, and therefore considering the equivalence relation as the one given by remainder, right, when divided by a number. So in that sense, the second example is analogous to looking at remainders after division by 1.
Okay, sir. But sir, if we see with respect to the number of elements in group, so means in first example it is look like a division by 1.
No, see what do you, so division by 1, when I'm saying division by 1, I'm looking at remainders. Okay, I'm not trying to divide
Yes,
the elements.
that I got it by remainder.
Right.
But sir, if we look at number of elements in D3 and the quotient group of D3 with respect to identity, then it in for example it looks like division by 1.
So because you are not looking at the right relation, right? The way I'm constituting this relation is by looking at the remainders obtained after dividing by a particular number. Okay, so if you look at the right in the first example, what you're seeing, I hope, is that none of the elements are equivalent. Okay? Each element is distinct in the given relation. All right.
Yes, sir, got it. Yes.
Okay. So these are sort of the two extreme examples. In sort of think of them, but anyways, they are interesting in their own right. Let's look at an example between these two extremes. Do you want to give me an example, or should I give you an example? One example surely was there in last week's tutorial. Can you pick up? Maybe let's take this example there. Z to Z5. So it's exactly this division by integers that I'm going to do. F of x is x mod 5. Okay, so this is the map I'm going to consider. Okay, so what is the kernel? No. Okay, before that, I hope all of you agree that F is a homomorphism.
Yes, sir.
Okay, again, I keep on hearing the same 2-3 voices. I hope I don't need to prove it. Or do you want me to prove it? Okay, I'm going to assume all of you are okay. I'm convinced that this F is actually a homomorphism. What is the kernel of F?
All multiples of 5.
And multiples of 5. What is the property of that set in Z?
5Z.
5Z. So it's a subgroup of Z, right?
Yes, sir.
Okay. So then, what is Z? 5Z. And what is FZ?
That is Z5.
FZ is Z5, right? It's an onto homomorphism, isn't it? So what the first isomorphism theorem says is that Z quotient with phi Z is isomorphic to Z5. To give you a clearer picture, let's look at the right Z. Okay, so this was your Z. What are you doing now? You're mapping them to Z5. What is the mapping? Something like this. Minus 9 goes to 1, goes to 1, goes to 1. Minus 8, minus 3, 2, 7. Right? And what is the kernel? And so on, right? And I'm not going to draw more arrows. What is the kernel? All multiples of 5, right? And what are the different cosets going to be in Z?
5Z, 5Z plus 1.
5Z plus
5Z, 3Z plus 1, 5Z plus 2, 5Z plus 3, 5Z plus 4. Okay, so first of all, realize that cosets in Z are not Z5. Okay, I hope this makes sense. Right? Cosets
Sorry,
are,
sir.
what I
Can
am
you
trying to say is, yes. So the quotient group in Z of the subgroup phi Z is what we have just written down here, right? Phi Z plus 1, phi Z plus 2, phi Z plus 3, phi Z plus 4. Now, be careful in the sense that this is not exactly equal to Z5. Okay? By not exactly equal to Z5, I mean as sets. Okay?
Yes, sir.
Right? This is not Z5, but as far as again bringing all of you back to the first class, as far as the interrelationship between these cosets under the group operation addition is concerned, this set of cosets in Z behaves exactly the same way as if elements in Z5 behave. Okay, so the interrelationship amongst the cosets is the same as that of Z5. Okay, so as sets Z5 and Z quotient phi Z are different, but as groups they are isomorphic and can be considered as the same. Okay, am I making sense?
Yes, sir.
Yes, sir.
Okay, do you want more examples or you're sort of happy with this? So, no issues. So then I'm assuming that this is clear. Then we move on to the next result. So what we did as of now is we looked at a homomorphism F from G1 to G2. Okay, then we obtained kernel of F and we showed that showed that we can obtain a new group, right, by taking the quotient of G1 with the kernel of F. And then we showed that this is sort of isomorphic, right? G1 kernel F with F G1, which let us assume is equal to F, is equal to G2. Okay, so this is isomorphic, this is a homomorphism. Okay. What can we say about these two? G1 with the quotient group in G1. What can be the relation? Okay, that is what proposition 28 addresses. Okay, so what it says is, and this is a slightly more general result. Remember in theorem 2, right, we were specifically looking at the quotient group with respect to the kernel of a homomorphism, which happens to be a normal subgroup also. Okay, but it is just one example of a normal subgroup in G1. Okay, since the idea is to create or to convert this homomorphism F into an isomorphism, therefore we used its kernel. As far as proposition 28 is concerned, it is just looking at the relationship between G1 and quotient group. Remember, you can obtain a quotient group only if the subgroup that you are considering is a normal subgroup. Right? Otherwise, the group structure will not hold. Okay. G1 slash K is a group only if K is a normal subgroup in G1. Okay. That I hope you will recollect from the last class.
Sir,
Okay. So
otherwise,
proposition.
if not normal subgroup,
Then if it is not normal subgroup, then would the set of cosets be closed?
They may not be close.
They may not be closed, right? In fact, if it is closed, then that K, it has to be a normal subgroup, isn't it? We had showed that this is an if and only if condition, isn't it?
yes, sir.
Okay, so if K is not a normal subgroup, then G1 slash K will not be a group. Okay, so please remember, normal subgroups are important. Okay, if you want to have a quotient group, right, then the subgroup you are considering must be a normal subgroup. Okay, and kernel of a homomorphism is one example. Okay, but proposition 28 is slightly more general. says that if I pick any normal subgroup K in G, okay, then there exists a homomorphism phi between the original group G and the quotient group. Moreover, the homomorphism is an onto homomorphism because, of course, give me two groups, the trivial homomorphism always exists. Okay, so in that sense, this is a non-trivial homomorphism. It can be shown that this homomorphism is onto the quotient group, and the kernel of this homomorphism is your normal subgroup. Okay, the statement understood?
Yes, sir.
Then let's go ahead and prove this. And the proof is very easy to see. What should be the homomorphism? Can anybody guess? The kernel is already given to you. Okay. So I want to define phi between G to G, the quotient group, such that phi maps K to, where should phi map K to? Remember, K is a normal subgroup of G. Where should this
Set
go
of
to?
elements of K.
Should go to EK. Right? This is sort of making it explicit that what I mean by EK is should go to the coset K. Okay, now can you define what the homomorphism would be? What should this be? See, what should happen? Phi AB should be equal to phi A phi B. Given that K is a normal subgroup, you know phi A is a coset, phi B is a coset, right?
Yes, sir.
And
Yes.
phi AB should also be a coset. So what should the mapping be, given that this has to be true? What happens with this definition? There are three things to verify with this definition of map phi. One, is it well defined?
Yes, sir.
Why? Sort of takes an element to the coset in which that element is there. Is this making sense?
Yes, sir.
Is this a homomorphism? What is phi AB?
AB.
ABK.
ABK. What is ABK?
Phi A into phi.
So that is what you have to show.
AKB.
AKBK.
This is AKBK. You can see the role of K being a normal subgroup here. This is true only if K is normal subgroup.
Normal.
Okay. What is AK?
Pi.
Pi. Okay. Pi. Next, what else do we have to show? What is the statement of the proposition?
Onto.
Need to show that pi is onto. So is it onto?
Yes, sir.
Okay, so in order to show onto, let us arbitrarily pick an element in the codomain. Codomain is nothing but set of cosets. Okay, so we arbitrarily choose a coset. But since it's a coset, then G is an element in the group G, right? And so
Yes, sir.
phi of G is by definition equal to GK, which implies phi is onto. Any issues here? Again, maybe if you take a look at this example, it might be more clear. So this, I hope, is clear, right? That the quotient group is isomorphic to Z5. How about these two? So you made cosets from Z, right? Now, what is the property of cosets? Is going to partition the original set, isn't it?
Yes, sir.
So if I map an element to its coset, that mapping by definition is onto, isn't it?
Yes, sir.
Yes, sir.
It is onto.
Right? I mean, it's just logical that cosets partition the original set. All I'm doing is taking an element and putting it in the right coset. Therefore, and since this mapping is defined on the entire original set, this mapping has to be onto.
Yes, sir.
Right? How about homomorphism? That comes from the fact that these partitions are derived from a normal subgroup. Okay, so maybe let's take another example. That this is clear. Which example should we take? You want me to take any specific example, then I can do that. Otherwise, okay, we'll do one thing. We look at the next set of results, right? Because then I think it will help you generate more examples. Okay? I think that would be a good idea. We have seen what happens if we have a normal subgroup, right? With a normal subgroup, you can construct a quotient group. okay, which is sort of sorry, not isomorphic, but which is homomorphic to the original group. Moreover, if that normal subgroup is kernel of a homomorphism, using that you can turn that homomorphism into an isomorphism, right? So that is sort of emphasizing the importance of normal subgroups. Now, how to identify or how to characterize normal subgroups? Okay, I know how to characterize a subgroup. Let's now try to see what conditions is that subgroup going to be on normal subgroup. Okay, so that's your next proposition, number 29. Okay, so the first statement, the first way to figure out if H, which is a subgroup, is also a normal subgroup is H is a normal subgroup of G if and only if the set G H G inverse. Okay, this is a subset in G, right? If this is also a subset of the subgroup H, and that also, this G cannot be only few specific elements of the group. For every element G of the group G, if G H G inverse is a subset of H, then H is a normal subgroup. And this is an if and only if statement. If H is a normal subgroup, then this will also happen. Okay, let's quickly prove this. Things to prove, let's first go this way. So if H is normal subgroup of G, we need to show that GH G inverse is an element in H. Okay. In order to show that, we'll just pick an arbitrary element in GH G inverse. Okay, so how do I write this arbitrary element as? X will be equal to
GH1 G.
GH1 or GH G inverse, where H is some element of the subgroup. Okay, now what can we say about HG inverse?
So it belongs
G
to
inverse.
the right coset.
It also belongs to the right coset. So therefore, there exists some element H1 in H such that HG inverse is equal to G inverse H1. That implies X is equal to G inverse H1, which is equal to H1, and H1 is an element of H. Therefore, GH G inverse is a subset of H. Right? I hope the proof is clear. How about the other way around? This is given. What do we need to show in order to show that H is a normal subgroup of G? Definition?
GH is equals HG.
Right. So left coset is also a right coset. Okay. So again begin with an element of the left coset. Okay, and I want to show that this is also an element of the right coset and vice versa. Let's just write this down. Okay, so this implies X will be equal to some GH okay. Next,
Yes.
what will we do? I need to use this, right? You can see I have GH, right? So let us try and see what is XG inverse. What will this be? This GHG inverse. What can we say about this element? GHG inverse?
That belongs to H.
Belongs to H.
This belongs to, of course, I will of course slowly. GHG inverse by definition, which is given to be a subset of H. Therefore, XG inverse is equal to sum H1, which is an element in H, which implies X is equal to
H1G.
H1G, which is an element of the right quotient. Therefore, GH is a subset. Happened. Crashed. Okay, I hope the screen is visible.
Yes, sir.
Similarly, I think you should be able to show that HG is a subset of GH, right? The proof is exactly the same. Okay, in that case, when you start with HG, an element in HG, you will have X equal to HG, and then you will pre-multiply by G inverse to get G inverse X equal to G inverse HG. Okay, but you can carry forward using the same argument. Okay, is that fine?
Yes, sir.
Yes, sir.
Yes, sir.
So assume you can prove HG is a subset GH, which implies G. This is of course for every G. Therefore, H is a non-G. Okay. So that's the first way to figure out when do we have a normal subgroup. Next way is basically the same thing. Right? It says that GHG inverse is not only a subset of H, but it is exactly equal to H for all group elements. Okay? Is that all right? So if I want to show the second result, what do I need to show?
Both are
H is a
subset.
subset of
Each other,
GH
right?
inverse.
And GHG inverse is, we have already shown that it is a subset of H. Okay, so what do I need to show?
Subset of GHG.
Exactly, show that if H is a normal subgroup of G, then H is a subset of GHG inverse for all G. How do we show that? So let's just start from what is given to us. Okay, so let H be an element of H and G be any arbitrary element of G. Okay, what can we say about G inverse HG?
belongs to
Belongs to?
GHG inverse.
No, it does not belong to GHG inverse. It belongs to?
Belongs to H.
Yeah, but how? Because it belongs to G inverse HG, right?
Yes, sir.
And we know that for all elements G, GHG inverse is a subset of H. So it also has to be true for G inverse HG. Okay, so this is a subset of H. Okay, please remember, I hope you see the difference. I cannot directly write G inverse HG is an element of GHG inverse. Right? So since this is a subset of H, G inverse HG is equal to sum H1 in H, right? Then I think we are done, isn't it? What can we say about H?
It will be GH1 G inverse.
And so this is an element of GHG inverse. Therefore, H is a subset of GH. Inverse. Okay. The other way around, I don't need to prove, right? Because I've already shown. So the second condition is a stronger requirement, that GHG inverse is equal to H. Since it is equal to H, it automatically implies GHG inverse is a subset of H. If it is a subset of H, in the first point in proposition 29, we have already proved that H will be a normal subgroup of G. Okay, so that takes care of it. The next two are sort of small interesting nuggets. Okay, one way to identify that a subgroup is a normal subgroup is if the index of this subgroup in the group G is equal to 2. Okay, sort of looks a little strange. What has this got to do with subgroup being a normal subgroup? And by the way, please note this is not an if and only if statement. Okay, but if H has an index equals to, then that subgroup has to be a normal subgroup. Why should that be the case? Can anybody see that? What do I need to show in order to show that H is a normal subgroup? Left coset is right coset, right? What are the left cosets? Quick.
GH where G belongs to.
No. G, acha, G, small g. Yeah, but in this case, what is given to you? How many distinct cosets are there?
2.
2. So, out of these two, what would one coset be?
One is H.
One is H. And the other, let's say, is AH, where, what do we know about A?
A
belongs
is
to
not
G.
in H but in
A
G.
is not in H, but A is in G. Okay? Plus, what do we know about this? This is from your discrete math course. This is equal to G and there is no intersection, right? What are the right cosets? One right coset is H. What is the second right coset? Has to be HA. No, not HD. I mean, HD is also okay, but it also is the same as HA, right? Because A is not in H. Is that clear?
Yes, sir.
Then the same thing, H union HA is G, H intersection HA is phi. What can we say about HA and AH?
Both should be equal.
Both should be equal as desired. Therefore, H is a normal subgroup of G. Because of course the second left and or the first left and right cosets are H, which is one and the same. Okay, so both left cosets and both right cosets are one and the same, which is the definition of normal subgroup. Can you see examples of this?
Yes, sir. D3.
3. Okay, what is the? Can you give me one normal subgroup of T3 according to this?
I R square.
IRR square. Right. Group is T3. Example 1. H R square. Right. So that there would be only two cosets. We don't even need to write what the cosets are. Therefore, which is a normal subgroup of G. Any other example? G is Sn. H is the alternating group. So the subgroup containing all even permutations. Okay, we know that the order of H in factorial by 2, which is the order of Sn by 2, implies I Sn An is equal to 2, which implies that the alternating group of order n is a subgroup of Sn. And several such examples, I think. Easy one is this, Z8, and H is 6. Z8. Okay, again, the order of H is 4, so therefore I 2Z8 in the group Z8 is 2, which implies 2Z8 is the normal subgroup of Z. So you can see that even though it looks like a very small result, it sort of gives us a lot of nice normal subgroups. Let us look at the fourth and the last characterizing property of normal subgroup. Again, this is not an if and only if statement. It says that if H is the only subgroup of a particular order, then that subgroup has to be a normal subgroup. Okay, once again, this statement, the way I've written it, may appear a little confusing. What it says is, if I give you a subgroup, it will have a certain order. Okay? If there is no other subgroup of that same order, then that subgroup necessarily has to be a normal subgroup. Okay, let's quickly prove this. Why should that be the case? Okay, what can we say about the number of elements of GH G inverse.
Same as
Same as H.
Sure?
yes, sir.
Okay. I mean, so right now I'm not proving it. I'm assuming you can prove it. Okay. Then what can we say about this set GH G inverse for any G? For any G in G, what is special about this subset? So in other words, so let x1 be G H1 G inverse, x2 be G H2 G inverse. Okay, be two elements in G H G inverse. What can we say about x1 x2?
H1, H2.
x1 x2.
Sir, it is
Will it be
X3 where
It is close.
GH3 G inverse.
GH3 G inverse, right?
Yes, sir.
Or H1 H2 G inverse. So this also is in GH G inverse.
Yes, sir.
Yes, sir.
So in other words, GH G inverse is closed.
Yes, sir.
How about inverse? So let X be GH G inverse. Okay, then GH inverse G inverse also belongs to GH G inverse.
Yes, sir.
What
And it is inverse of
is
X.
exactly? Okay, X inverse is nothing but GH inverse G inverse. So therefore, what have we shown? GH G inverse is
Subgroup.
A subgroup.
subgroup of G. Now can you complete the proof? See the number of elements in this subgroup, right? GHG inverse for every G is the same as the number of elements in the subgroup H. But we have also said that H is the only subgroup of that order.
GH inverse is equal to H.
Exactly. And that is true for all G.
Yes.
And then that is basically the second point. Therefore, H has to be a normal circle. That clear?
Yes, sir.
Yes, sir.
Then I think we finish this class with one definition. So we have seen that for normal subgroups, it is important. Oops. G. For every element of the group G, H G inverse must be equal to H. Okay, but let us assume there is a group H right? For which G inverse is equal to H only for a subset of the group G, not for all group elements. Okay, let us try to examine the properties of this set of elements of the group. Okay, that set, right, contains all elements of the group G, for which G inverse is equal to H for a given subgroup H. Okay, that set is what is called the normalizer of H in G. Okay, and the notation is NGH. Okay, once again, remember, if I have a normal subgroup H, then this property G inverse is equal to H is satisfied by all group elements. Okay, but in the definition, please be careful. I did not assume H is a normal subgroup. It may so happen that only a few elements G of the group capital G satisfy G inverse equal to H. Let us consider that state. Okay, that set is what is called normalizer of H. Of course, if H is a normal subgroup of G, then what can we say about the normalizer of H in G?
The group itself.
Will be the group itself, right? So that's one important result we already have shown. Now this set, okay, irrespective of whether H is a normal subgroup or not, you can show that it is a subgroup of G. Okay, and I'm not going to prove this. I think it's very easy to show this. Okay. Yeah, I don't have time as of now. What you can also show is that the normalizer of a subgroup H is much larger than the subgroup H. Okay, why? Because of course, if I take any element H in H, okay, what is H? H inverse
H itself
is equal to H. So therefore, what have we shown? That this subgroup H is a
subset of normalizer.
Subset, and of course it will also be a subgroup, right?
Yes.
Of this. Right? Not only this, H has to be a normal subgroup of NGH. H may not be a normal subgroup of G, but it will surely be a normal subgroup of NGH. And I think it's very easy to see because of the way NGH is defined. Right? It is defined using the property of normal subgroups. The NGH will contain only such G's such that G inverse is equal to H, right? And that is the condition for a normal subgroup. Okay, so I think it is easy to prove that H will be a normal subgroup of NGH. Third property. Okay, so if I give you a group G, okay, and I give you some subgroup of this group G, let's call it K, and I give you a smaller but a normal subgroup of this subgroup K. Okay, remember H given here is assumed to be a normal subgroup of K, not necessarily of G. In that case, the normal subgroup of H will be a larger set than K, larger or the same set. Okay, again, I think all you have to do is to use the definition and prove this. And the fourth result is something we have already proved. Okay. H, if H is given to be a subgroup of G, then H is a normal subgroup of G if and only if the normalizer of this subgroup H in the group G is equal to the entire group. Okay, so roughly given you the proofs of 1, 2, and 4. 3, I think, is easy. Just need to work it out. Okay, not very difficult. Okay, so I would like to stop here for today. I'll just mention 2 things about the exam. Okay, first thing is I will give you the list of all propositions and theorems that are there in the slides in the exam itself. Okay, so you need not mug up anything. All right, that's the only announcement I think I have. Apart from that, there's one more small surprise, and that is that we're supposed to give a surprise quiz right now. Okay, so you can go to the Moodle page. There are 5 questions for you to answer. Okay, you get 8 minutes to answer those questions. And yeah, so the quiz pattern is similar to your first quiz. Okay, it will be visible in just a minute. Right, so if somebody could go to the Moodle web page and see if you can attempt the quiz and let me know. Once you do that, I will end this class. Wish you all the best, not only for the quiz, also for your mid-sem exam. In case you have doubts during the weekend, you can send me an email. I will try to respond at the earliest. So could somebody give me a quick confirmation of the
Yes,
quiz?
sir, it's visible.
Visible, and you can attempt it, right?
Yes, sir.
Okay. Thank you. All the best.